we used the Laplace transform in a previous lecture to solve the transient problem of a half sine pulse being applied to a mass spring system. We can also use the convolution integral and end up with the same answer. So in this lecture, I'll do basically a reduced version of the solution, and I'll explain what I mean by a reduced version of the solution using the convolution integral. Well, what we saw was when we dealt with the Laplace transform, we actually saw that for this sine pulse, which only varies between 0 and t naught, then the solution for xt, there was a solution for xt where t was less than or equal to t naught or greater than or equal to 0, which was the solution between this region here. And then we saw that there was a solution for xt when t was greater than t naught. And actually, either of these solutions depended on the response found within the pulse between 0 and t naught. The solution of this when t was greater than t naught was basically just using a time delay of the solution for the region 0 to t naught, and then solving that problem. So in other words, the only point I'm making is that as long as I were able to find the response between 0 and t naught, then if I find xt between 0 and t naught, then I can go ahead and I can basically solve the entire problem for t is less than or equal to t naught, greater than 0, and also t is greater than t naught. So what I'm going to do is use the convolution integral to only solve between this region here, 0 and t naught, and you'll see basically how that works. So just to be clear, we're going to use the convolution integral, right? And I'm going to focus on the time t, so less than t naught, less than or equal to t naught, but greater than or equal to 0. And what we'll do is we'll say that, well, what is the equation of motion? Well, we already saw, you'll need to look back at the previous lecture, but we already saw that the equation of motion is simply mx double dot plus kx is equal to, and it was f naught sine omega t between t is less than or equal to t naught, 0 and 0, t is greater than t naught. This is just written like this for completeness, and omega was equal to pi on t naught. Again, all these are things we discussed before. But if I want to use the convolution just for this region here of t is less than or equal to t naught greater than 0, then really what I'm interested in is just the equation mx double dot plus kx is equal to f naught sine omega t. And I'm not going to substitute pi on t naught. I can do that down to the end, right? At this point, we want to remember, well, what is the convolution integral? Well, the convolution integral tells me that xt, the response is going to be equal to 1 divided by m omega n, the integral of f tau g t minus tau d tau. And if I rewrite that, and this is something you need to learn, then it just becomes 1 on m omega n integral f tau sine omega n t minus tau. That's what gt minus tau means, right? It's this sine term that you're looking at here, d tau. And we integrate that between limits 0 to t and 0 to t. So what is f what is f tau going to be? Well, what I can say is this. I can say, well, listen, I know that, so again, I'm only interested in time t is less than or equal to t naught, greater than or equal to 0. So this ft was actually just f naught sine omega t. And I'm not going to drop in omega is pi on t naught. I'm just going to leave it as sine omega t. But if I want this is t here. If I want this in terms of tau, then f tau basically is just the same expression with t substituted for tau. So you'll end up with sine omega tau. It means, therefore, that this convolution integral, what it becomes is just going to be xt. It's going to be 1 on m omega n remains unchanged. The integral of 0 t, and then you're going to put in f tau here, sine omega tau, and then what you're going to do is you're going to put in this expression, sine omega n t minus tau, right? So then you're going to come in here and you're going to say, well, I have a sine term, omega n t minus tau. And I want to integrate that expression with respect to d tau. So how do I integrate that expression? Well, I need to use an identity, and that identity it's a trigonometric identity, but that trigonometric identity just tells me that, well, if I have a sine x sine y term, product form like that, it's going to actually be a half cosine x minus y minus cos of x plus y. And really, if I use that identity, you could kind of recognize that, well, xt is going to be equal to 1 on m omega n 0 t. F naught comes on the outside, right? So maybe I could just put f naught out here. And 2, which remember I'm going to use that identity here. So this 2 can also be on the outside, can't it? Yeah. So now we can use the identity. Well, I can say x is really omega n tau. So maybe I can say cosine, open that bracket, omega tau minus omega n t minus tau. And then I can say, well, this minus sign is going to come here, so minus cos. Then again, I'm going to have omega tau, but now I'm going to have plus omega n t minus tau. And that entire expression is going to be integrated with respect to d tau. I'm not really going to put, maybe I should put it just to be clear, but this entire expression is going to be integrated with respect to d tau. And to do that, I'll use some substitutions. I'll say, well, listen, maybe u is equal to cosine, sorry, yeah, so maybe u is equal to omega tau minus omega n t minus tau, and maybe, which is this term here, and maybe v is equal to omega tau plus omega n t minus tau. So a small incremental change du is going to be equal to really omega plus omega n d tau. It's just the differential of du with respect to tau, and represent it like this. And dv, incremental change dv, is going to basically be omega minus omega n d tau. So we use these substitutions, and you can recognize now, well, xt is going to just be f naught on 2m omega n. Integral, I'm going to leave out the limits because I'm changing everything to u and v now. So I'm going to get cosine of u for this expression here. But then what I want to do is I want to say, well, I want to, if I'm going to change this to u, I want d tau to be in terms of du. So then I'm going to change d tau to really, and I'll put it in yellow. I'm going to change it to du, d tau to du. So you just use that substitution. It becomes du divided by, because remember, d tau is going to be du divided by omega plus omega n. So now we can just put a little bracket here, and we'll put in a minus sign for this minus sign here, and then we'll start with the new integral, which is just going to be cos, and then I'm going to put v now because that's what it is, cos v, and again I want to change d tau to really dv, and it's going to be divided by omega minus omega n. And I'm leaving out my limits because the limits will now be between with the variables of u here and the variables of v here. So you do that and you very easily you recognize, well, listen, xt is going to be equal to f naught on 2m omega n. If I integrate cos u with respect to du, I'm just going to get sine u, divided by omega plus omega n minus sine v of omega minus omega n. And I have some limits here for u and v, but I'll sort of get the u and v back into the t terms. So I'm going to say, well, xt is going to be equal to f naught on 2. Xt is going to be equal to f naught on 2m omega n. Omega n, and then put that bracket in here. I'm going to put sine, but now I'm going to substitute what u was. You remember what u was? U was equal to this omega n, this omega tau term, omega tau term minus omega nt minus tau, omega tau term minus omega n, which is tau, t minus tau term here. And this entire thing was divided by omega plus omega n. And then, see if we could get some space here, but you're going to have this minus sign again, and you're going to have sine. It just was omega tau plus omega n t minus tau divided by omega minus omega n now. And now I can sort of put in my limits because I wanted tau to be between 0 and t. So we can substitute, we can sort of substitute for your limits now, and what we'll end up with is just what you're going to end up with is just, well, let's do it, omega plus omega n. When I substitute tau, remember it's tau you're substituting for, not t. When tau is equal to t, then t minus t is 0, and tau is equal to t here, you actually just end up with sine omega t, and then you put in this minus sign, and then you say, well, tau is equal to 0, so tau is equal to 0, you get sine of 0 minus omega n t, so it's actually going to be minus sine minus omega n t, right? And at this point I'm just going to take a little shortcut one time, because sine of minus omega nt is really minus sine omega nt, so I could actually just get rid of this minus sign here, bring it on the outside, and this sort of becomes positive. So I'm going to take that shortcut, but you can slow the video down and do it yourself. We're going to have negative, that didn't change, and then I have omega minus omega n, and at tau is equal to t, you're going to end up at 0 again, and you're going to have sine omega t once more, and then you're going to have negative, and then when tau is equal to 0, you're going to have sine 0 omega nt. So you just end up with sine omega nt. And I've put this one in brackets, but really all of them should be in brackets, right? Now we'll close that off. So we can simplify it, and the whole idea is to get it looking like that Laplace solution that we had before, but f naught on 2m omega n, and maybe what I could say is that, well, this is the same. If I looked at the getting a common denominator, I can get it as omega squared minus omega n squared, and in that way it just becomes sine omega t plus sine omega nt multiplied by omega minus omega n, and then I can say minus, put a bracket here, and I'll have if I bring this across up here, it's going to be minus sine omega t, because I've taken the minus on the outside here. I'm going to have to see need a little bit of space again, so what I'll do is I'll just recognize that this should be omega plus omega n, and this is really the expression for xt. And you can see how it sort of simplifies. If you do the algebra, you can see that it sort of simplifies quite easily. It becomes f naught on 2m omega n. I'm going to just put this multiplied by, and put omega squared minus omega n squared here. But you can recognize that the sine omega t term multiplied by omega is going to basically disappear because of minus sine omega t by omega. And sine omega t by minus omega n is going to be added to minus sine omega t by omega n, so we'll end up with basically minus 2, and you can expand it and do it maybe better. And the sine omega n t term multiplied by omega n disappears because you have a minus sine omega, a plus sine omega n t term multiplied by omega n here, so you are going to end up with again plus 2 omega sine omega nt. So I'll sort of leave it up to you to expand and actually sort of see where that expression comes from and what disappears and what remains. We can say, well, xt is actually going to be equal to f naught on 2m omega n. Then I want to say, well, I don't want omega squared minus omega n squared. Actually, what I want is omega n squared minus omega squared. So really, this is the negative that we have on the bottom here. So we can actually get that, make on top here negative as well, just to get rid of that potential negative sign on the bottom. So just some algebra, but becomes 2 omega n sine omega t minus, changes sign now, 2 omega sine omega nt. And so you end up with this expression here. Sort of see that these two cancels out immediately. But you can start simplifying it a little bit. And you can recognize, well, it's going to be f naught divided by m omega n. I'm going to sort of write this a little bit differently now. I'll put omega n squared minus omega squared here. Then I'm going to say, well, this is really omega n sine omega t minus omega sine omega nt. And of course, if since k is equal to m omega n squared, right, and r is equal to omega on omega n, then you can even recognize that this expression gets a little bit closer to what we did before, where it becomes f naught on k omega n dot 1 on 1 minus r squared. And I'll leave you to kind of work out the algebra because what I've written here is actually the exact same thing as this, right? So you can do that because it's just to factorize out omega n squared, but you could do that aspect of it. It's just multiply it now by omega n sine omega t minus omega sine omega nt. And I believe for the Laplace solution, what we did was we said xt was equal to f naught on k 1 minus r squared multiplied by, now I'm going to put a little bracket where I'm going to say omega n sine omega t minus omega sine omega nt divided by omega n. I think that is how we had it. And so I'll sort of write that solution in the exact same way that the Laplace solution was written, just for completeness. But the Laplace solution was written in terms of f naught k 1 minus r squared. And what we recognized was that, well, omega n is a constant. Omega n is a constant, but omega could be written. Omega could be written in terms of pi on t naught. Remember that? So omega could have been written as pi divided by t naught. And we basically had this entire expression divided by omega n. What is this solution valid for? What time range? This solution is only valid for, just to be very valid for only t is less than or equal to t naught, greater than or equal to 0. But you can go back to that Laplace video that I did for this problem, and you can recognize that this is the only solution we need to move on to solve the entire problem. We of course take into consideration time delay and basically use superposition to solve the problem. But the idea is that convolution and Laplace leads us to what xt is for that pulse between t naught, t is t less than or equal to t naught but greater than or equal to 0, and then we can use this result to find the result for when, and I'll write it in blue here, when xt occurs at a time t greater than t naught, but we can really use this result. So go back to that Laplace video, and you'll sort of see that.